In DSP, signals matter because measurements are useless until they are represented clearly. 1.191 Mathematical representation of signals gives engineers a clean way to describe what is happening. That matters when audio, sensors, or communication signals have to be processed reliably. If the representation is sloppy, the later math solves the wrong problem. Think about a microphone waveform entering a DSP chain. The system only understands it after the signal is described in a usable form. That description lets you compare, filter, compress, or detect what matters. So this topic is really about turning a physical behavior into something engineering can act on. Once that picture is clear, the rest of DSP becomes much less mysterious. And that sets up 1.1. The core idea behind signals is simpler than it first sounds. 1.12 Physical representation of signals is just the engineering view that makes the concept usable. You start with a real phenomenon and choose a representation that preserves what matters. That might mean amplitude over time, a sequence of samples, or an input-output rule. The goal is not fancy notation. The goal is a model you can analyze, simulate, and implement. For example, a voltage trace becomes data only after you decide how to describe it. That description is what lets later DSP tools operate correctly. So the big idea is controlled representation, not raw observation alone. And that will matter again when you connect this topic to 1.12 physical representation of signals. When students get lost in signals, it is usually a notation problem first. 1.1.3 Deterministic and random signals tells you which variables describe the signal, system, or model. Time, sample index, amplitude, and units are not decoration. They tell you what kind of object you are actually working with. If you mix them up, continuous and discrete viewpoints blur together. A waveform x of t does not mean the same thing as a sampled sequence x of n. Engineers watch those symbols because they change the tools that are valid. So read the variables before you read the equations. That habit prevents a lot of avoidable DSP mistakes. And it makes the next idea, 1.1.3 physical representation of signals, much easier to follow. A good way to think about 1.1.1 mathematical representation of signals is as a translation layer. The physical world is messy, but DSP needs a clean internal picture. Signals provide that picture. They turn motion, sound, voltage, or data into something you can reason about step by step. Imagine sketching a moving signal onto graph paper so a computer can work with it. The sketch is not the real world itself. It is the model that keeps the important behavior visible. Once you have that mental picture, the later math feels less arbitrary. You can see why each symbol or operation exists. And that intuition carries directly into 1.1.42 physical representation of signals. Here is the basic way engineers reason through 1.12 physical representation of signals. First, identify the physical quantity you care about. Next, choose how it should be represented for analysis. Then decide which variables and units make that representation meaningful. After that, check whether the model keeps the behavior you actually need. Only then do you start doing DSP operations on it. This order matters because a bad representation poisons every later result. A clean setup makes filtering, detection, or estimation much more trustworthy. So the process is observe, represent, label, and then analyze. And that process carries forward into 1.12 physical representation of signals. Take a simple DSP example built around 1.13 deterministic and random signals. Suppose a sensor produces a changing voltage over time. Physically, it is just energy varying in the world. For DSP, you represent it as a signal with amplitude tied to time or sample number. Now you can compare peaks, timing, and trends in a repeatable way. If the same sensor is noisy, that representation still gives you something analyzable. That is the real payoff of this concept. It converts intuition into a form that algorithms can use. Once that is clear, harder DSP tools feel like extensions instead of magic. And the same logic shows up again in 1.12 physical representation of signals. When you look at a diagram for signals, focus on what is changing and what is fixed. 1.1.1 Mathematical representation of signals usually becomes clear when you track the axes, labels, or flow of information. A graph tells you which variable moves and which one organizes the view. A block diagram tells you where the signal enters, changes, and leaves. That is why pictures matter so much in DSP. They make the abstract structure visible before the equations arrive. If you can explain the picture in plain language, you probably understand the concept. If the picture feels confusing, check the variables before blaming the math. Engineers read diagrams as compact reasoning tools, And that visual habit helps a lot with 1.12 physical representation. In code, 1.1.2 physical representation of signals shows up as a representation choice before anything else. Python or MATLAB cannot process a physical event directly. They process arrays, sequences, and well-defined variables. That means signals become a software design issue too. You need the right indexing, units, and assumptions before the algorithm is trustworthy. A sampled sequence with the wrong interpretation can break an otherwise good routine, so implementation starts by matching the code representation to the real phenomenon. Once that mapping is right, DSP libraries and custom code behave much more predictably. This is why representation is not separate from implementation. It is part of the implementation mindset itself, just like 1.1.2 physical representation. You see 1.1.3 deterministic and random signals everywhere in engineering DSP work. Audio systems need it to represent sound before filtering or compression. Radar and communications need it to describe signals before detection or decoding. Sensors need it so raw measurements become analyzable data. Image and control systems rely on the same habit of structured representation. The common thread is simple. Real-world behavior has to be expressed in a form that algorithms can trust. That is why this idea survives across so many different applications. It is a foundational engineering move, not a niche detail, and it naturally connects to 1.12 physical representation of signals next. A common mistake with signals is treating a representation as if it were automatic. Students often jump to equations before deciding what the signal or model really is. That leads to mixed variables, wrong assumptions, or the wrong DSP tool entirely. Another trap is blending continuous and discrete viewpoints without noticing. The fix is simple. Name the physical quantity, the representation, and the independent variable first. Then check whether the model matches the engineering question you actually care about. That small pause prevents a surprising number of later errors. In DSP, setup mistakes are often more dangerous than arithmetic mistakes. And avoiding that trap makes 1.2 physical representation of signals easier to learn. The useful way to compare 1.12 physical representation of signals is to ask what changes and what stays fixed. Nearby DSP concepts can look similar while serving different jobs. One representation may describe the physical signal itself. Another may describe how a system acts on that signal. The distinction matters because the analysis tools follow the role of the object. If you confuse the object with the operation, the interpretation falls apart. So compare them by purpose, variables, and engineering use. That approach keeps the boundary clear without memorizing disconnected definitions. Good contrast builds intuition much faster than isolated formulas, and that clearer boundary helps when you move into 1.12 physical representation. The big takeaway from signals is that DSP begins with disciplined representation. 1.13 deterministic and random signals is not just vocabulary. It is the step that makes later analysis meaningful. Once a phenomenon is represented well, you can model it, transform it, and implement algorithms around it. If that first step is weak, everything after it becomes harder to trust, so carry forward this habit of asking what the object is and how it should be described. That is the foundation under the rest of Chapter 1. It also explains why the next concepts do not appear out of nowhere. They are all extensions of the same representation first mindset. And that bridge leads naturally into 1.1.1.2 physical representation of signals.